Hi everyone. So we're just going to jump right into this with question 1. It says the equilibrium constant is given for one of the reactions below. Determining the missing equilibrium constant. So in the first reaction we have 2SO2 plus O2 yields 2SO3. Now what we want to do is we want to see what's different about the second reaction where we don't know the Kc. So the first reaction we do know the Kc, and the second reaction we don't. Well, there's two things that I can see here that are different. The first thing is, if we look here, SO3 is the product, and over here SO3 is the reactant, and the SO2 and the O2 are the reactants, and over here the O2 and the SO2 are the products. So this thing has been reversed. The other thing that we can see is that here we have 2, 1, and 2, and here we have 1, a half, and 1. So it's also halved. So this reaction is reverse and half of this reaction. So what do we do to the Kc? Well, in order to find the new Kc value, so the Kc of the new reaction, or the second or the bottom reaction, equals 1 over Kc. I'm going to call this old. Okay, why is it 1 over? Because we reversed the reactions. So instead of products over reactants, it's reactants over products, or we take the reciprocal. But it's also half, so we need to raise this thing to the 1/2 power, or simply take the square root of it. So it's 1 over the square root of 1.7 times 10 to the 6th. And when you do that, 1 over the square root of 1.7 times 10 to the 6th gives you 7.7 times 10 to the negative 4, which is choice letter E. Alright, number 2 says, the reaction below has a Kp value of 3.3 times 10 to the negative 5. What is the value of Kc for this reaction at 700 Kelvin? So, if you recall, Kp equals Kc times RT to the delta N, where delta N equals NF minus Ni. N is moles, and in this case Kp is pressure and Kc is molarity, basically. So basically we're looking for the change in number of moles of gas. So notice if things were not gases, in this case they're all gases, so it's just changed in the number of moles. But if something was not a gas, it would not count as moles. So let's take a look here. The final state, or the products state, we have 2 moles of SO2 and 1 mole of O2 for a total of 2 plus 1, which is 3 moles of gas. So it's going to be 3 minus, if we look at the reactant side, we have 2 SO3 and that's it, so 2 moles of gas, which equals 1 mole of gas, which is changing. Now we need to rearrange this, because in this case we're given the Kp, and we're asked for the Kc. So we have to divide both sides by RT to the delta N. And we find that Kc equals Kp divided by RT to the delta N. Okay, like that. So we already found delta N. That's going to be 1. So what are we going to do? Well, we're going to plug in our Kp, which is 3.3 times 10 to the minus 5. We're going to plug in our R value, which is going to be 0.08206. This is liter atmospheres per mole K, okay, times our temperature, which is going to be 700 K. I didn't write in the liter atmospheres, mole K. Multiply, and then all to the delta N, which in this case is just 1. When you do that math, you find that Kc is equal to 5.7 times 10 to the negative 7, that's a 7, which is choice letter C. Alright, so if you haven't watched the previous question, please start with that one. But it says, in which of the following reactions will Kc equal Kp? So remember from the previous one, Kp equals Kc times RT to the delta N. Note that if delta N is 0, RT to the 0 will just be 1. So if delta N equals 0, Kp equals Kc. Why? Because RT to the 0 is 1, so Kp equals Kc times 1, so Kp equals Kc. Remember that delta N is the moles of gas. If you have things in here that are not gases, then that's not going to work. So let's take this example. All right, I'm just going to put when on here. When delta n equals 0, Kp equals Kc. So let's take a look. Here we have 2 plus 6, which is 8 moles of gas on our product side, minus 4 plus 7, or 3, which is 7 moles of gas on this side. So we have 2 and 6 is 8, and 4 and 3 is 7. Delta n is not equal to 0, so therefore we are not going to have Kp equal to Kc. Let's take the next case. We have 2 plus 1, which is 3, and over here we only have 2. 3 is not equal to 2, so that's not going to work. Here we have 2 plus 1, which is 3, and then only 2 over here. 3 is not equal to 2, so that doesn't work. Let's check the last one. We have 1 plus 1, which is 2, and then we have 1 plus 1, which is 2. So we have 2 moles of gas on both sides. So since we have 2 moles of gas on both sides, the delta n is going to be equal to 0, and Kp will equal to Kc. Alright, number 4 says, determine the value of Kc for the following reactions if the equilibrium concentrations of HCl is 0.13, HI is 5.6 times 10 to the minus 19, and Cl2 is 0.0019. So let's take a look at this. Well, the first thing we do is we have the reaction here, so we want to write the Kc expression. Remember that in the Kc expression, we're only putting things that are gases or aqueous, so in this case we're going to leave out iodine. So it's going to be products over reactants. So in this case, it's going to be the concentration of HI squared times the concentration of Cl2 divided by the concentration of HCl squared. Okay, so this is going to be our values. Since we are given equilibrium concentrations, we don't need to fill this into the ICE table or anything like that. We can just plug in the values directly. So if we look here, we're going to take the concentration of HI, which is provided to us, which is very, very small, so 5.6 times 10 to the minus 16, and we're going to take that and square it. We're going to multiply that times the concentration of Cl minus, which in this case is 0.0019. We're going to take that and we're going to divide it by the HCl squared, and you'll notice the HCl relative to the other two is much higher. It's going to be 0.13 squared. Alright, so if we look here, the products are clearly favored. There's very, very small, the reactants are clearly favored. There's very, very small amounts of products on the top and a much larger amount of reactant on the bottom. So when we do this, we get 3.5 times 10 to the negative 32. So what you see is we have a very, very, very small value of Kc. It's much, much less than 1, right? 10 to the negative 32, it's basically 0. Alright, so this means that the reactants are favored here because the reactants are going to have a much higher concentration than the products. So that's why we have a very, very small value of Kc, but that doesn't ask us that, it just asks us for the value. The answer here is choice letter D. Alright, this one is very similar to the previous one. It says, consider the following reaction, equilibrium concentrations, and the equilibrium constant at a particular temperature. Determine the equilibrium concentration of H2O. In the previous case, we had to find Kc given equilibrium concentrations. In this case, we're given Kc and some equilibrium concentrations, and we need to find the other one. So the first thing we need to do is write the Kc expression. So remember that Kc is products over reactants. So in this case, the concentration of C2H5OH, ethanol, on the top, over the concentration of C2H2 ethylene, C2H4 ethylene, over times the concentration of H2O. So in this case, they're all 1, so no exponents here, they're all 1, and they're all gases are aqueous, so they all go in the equilibrium expression. In this case, we're looking for concentration of H2O. So what we want to do is plug in what we know. Well, we know Kc, 9 times 10 to the 3 is Kc, so I'm just going to plug that in, equals the concentration of ethanol at equilibrium. This is important, 1.69. Okay, we don't need to use an ICE table because these are not initial concentrations, they're equilibrium concentrations. The concentration of ethylene is 0.15. Sorry, 0.015. You can see that. All right, and then the concentration of water is what we're looking for. That's the unknown. Well, how do you do this? Well, the first thing you want to do is cross multiply. So 9 times 10 to the 3, 9,000 times 0.015, okay? And when you do that, you get 135 times the concentration of H2O, because that cross multiplies as well, so that's going to cross multiply through as well, equals 1.69. So that is basically just equal to that. Now you're going to divide both sides by 135, and you're going to get the concentration of H2O is equal to, where is it here? 0.013 molar, which is choice letter B. Alright, so if the previous problems weren't completely on the screen, I apologize about that. I have tried to zoom out a little bit, so now this is roughly as wide as my paper, so I can't possibly do that again without writing on the table, so hopefully that'll work out. Alright, it says, consider the following reaction. COCl2 gas is in equilibrium with CO and Cl2. The reaction mixture initially contains 1.6 molar COCl2. Determine the equilibrium concentration of CO if Kc for the reaction is 8.33 times 10 to the minus 4. Calculate this based on the assumption that this answer is negligible compared to 1.6 molar. So I just rewrote the reaction down here. Here we're going to need an ice table. Why do we need an ice table here and not in the previous case? Because in this case we're given the initial concentrations. In the previous two problems we were given the equilibrium concentrations. When you're given the initial concentrations, you have to use an ice table. So we're going to use initial, change, and equilibrium. Let's plug in what we know. Well, we know that the initial concentration of the COCl2 is 1.6 molar. Okay, we can also assume that the initial concentrations of these things are 0, because we start with initially just this, and then it reaches equilibrium, so it makes some of this and some of this. We want to know what's the change. Well, this is all 1 to 1, which is helpful. So we're going to subtract X amount of this, we're going to gain X amount of this, and gain X amount of that. When we have equilibrium, we're simply just going to do the math. So this one's going to be 1.6 minus X, but we are going to ignore this X, so we don't have to use the quadratic equation, and because we just look at the answers, they're way small compared to 1.6. They're way less than 5% of this value. Okay, these are all very small numbers. All right. It also tells us we can ignore this. In this case, you have 0 plus x, which is just x, and in this case, you have 0 plus x, which of course also is just x. Now we just write our Kc expression. All right, products over reactants. In this case, everything's a gas, so it all goes in there. So our first product is the CO. Our second product is the Cl2, and our reactant is COCl2, and they're all in brackets because we want the concentrations. Now let's plug in what we know. Well, we know Kc. Okay, it's 8.33 times 10 to the negative 4 equals these. We know, well, they're x's, x times x, which is just x squared, divided by this one, which is not 1.6 minus x, it's just 1.6 molar. Cross multiply, and we find that x squared is equal to this times 1.6, which is going to be equal to 0.00133. Take the square root of both sides, you can ignore the negative answer, and you find that x is equal to 3.7 times 10 to the minus 3 molar. This is the equilibrium concentration of CO. No, in this case, it also happens to be the equilibrium concentration of Cl2 because they're 1 to 1. So the answer here is going to be, all right, I apologize about that. I made a small mistake here. This should be 3.7 times 10 to the minus 2. Okay, which matches our answer here, which is choice letter B. I don't know why I wrote minus 3 on my paper here, but it should be negative 2 as the answer. All right, number 7 says, consider the following reaction at equilibrium. What effect will increasing the pressure of the reaction mixture have on the system? So if we look here, we have a solid and a gas, and a solid and a gas. So if we look at the gases, because the pressure is only going to affect the gases, we have 1 mole of gas on our reactant side, and we have 1 mole of gas on our product side. Specifically, the O2 is the 1 mole of gas on this side, and the SO2 is the 1 mole of gas on this side. So there's an equal amount of gas on each side. So what does a reaction do? Well, Le Chatelier's principle, which is what this question is asking about, tells us that the reaction will shift to minimize disturbances in equilibrium. So if you increase the pressure on a reaction where there's 2 moles of gas on this side and only 1 mole of gas on this side, the reaction will shift to decrease the pressure. So if there's 2 moles of gas over here and only 1 mole of gas over here, the only way the reaction can decrease the pressure when you artificially increase it is to make less moles of gas, so it'll shift in this direction. But in this case, this reaction actually can't solve this problem. It has no way to do that. So basically, if you increase the pressure, no effect could be observed. Why? Because it has no way to get rid of moles of gas. If it had a way to get rid of moles of gas, when you increase the pressure, it would do that. But because both sides have 1 mole of gas, there is going to be no change in the no effect will be observed in the reaction here because there's 1 mole of gas on both sides. All right, question 8, it's more of the same on Le Chatelier's principle. It says the following reaction is exothermic. What change will shift the equilibrium to the left? All right, so we want to shift the equilibrium in this direction to the left. Well, if this reaction is exothermic, we can think of heat as a product. Okay, we can think of heat as a product of the reaction because the reaction is giving off heat, so we can think of heat as a product. Well, Le Chatelier's principle says that the reaction will do what it can to disturb or to reestablish equilibrium. So if you increase the temperature, this reaction is going to want to get rid of that heat. It will get rid of that heat by shifting it in this direction. So increasing the temperature will shift the reaction in this direction. Okay, now let's see, so that's choice letter C. Let's see what will happen if we do A or B, because all of the above is an answer. So raising the temperature will shift it this way because the reaction wants to get rid of heat, and heat is a product in an exothermic reaction. What about removing O2? If we remove O2, the reaction will say, hey, there's not enough O2 in the system. We need to make more O2. Well, what's the only way that the reaction can make more O2? It's by decomposing the SO3 into SO2 and O2, or said another way, shifting to the left. So we talked about that one. This one will also cause the reaction to shift to the left. What about adding SO3? Well, if we add SO3, the reaction says, hey, there's too much SO3. How do I get rid of SO3? Well, I turn it into SO2 and O2, or said another way, I shift the reaction to the left. So all of these answers will shift the reaction to the left. So the answer here is D, all of the above. All right, it says consider the following reaction at equilibrium. What effect will removing NO2 have on the system? So the concentration of NO2 is going to decrease artificially. Well, Le Chatelier's principle tells us the reaction is going to do what it can to minimize the disturbance in equilibrium. So what the reaction says is, hey, there's not enough NO2 in the system because someone took out some of the NO2. Well, what's the only way the reaction can make more NO2 to compensate for the NO2 that is gone? Is to shift to the left, because it knows that if it reacts SO3 with NO, it can make more NO2 to replace what has been lost, okay, or taken out. So in this case, the reaction will shift in the direction of the reactants, which is to the left, because it wants to make NO2 when the concentration of NO2 is artificially decreased. So in the past 3 problems, we've talked about Le Chatelier's principle, and the major thing to remember is that whatever is artificially done to the equilibrium reaction will do what it can to restore order or restore equilibrium, or replace what is missing, or get rid of what is put in excess, or whatever the case